Before we can start writing programs, we first need to know what a computer is and how it functions. So what is a computer? The textbook definition says a computer is an electronic device which can perform a set of tasks based on the instructions given to it. Sounds really complicated, isn't it? But you can think of a computer to be very similar to a friend. Let's say you want your friend to do you a favor. You would just tell him what he needs to do and how it should be done. Now, if you're not clear in communicating to him as to what he needs to do, then he might just land up doing something totally different from what you wanted him to do. Let's say you wanted your friend's help to propose to a girl you really like, but you messed up while pointing the girl out. Then he might just land up proposing the wrong girl, and for all you know, this girl might even be someone you hate. So you really don't want to mess up while trying to tell what you really want. Computers are also very similar. If you want the computer to perform some task, then you need to tell it clearly as to what it needs to do. So what do we mean by clarity? To have clarity in any task, there are three components involved. There is the input, there is the task itself, and then there is the output. In this example, the input is the girl, the task is proposing, and the output could either be a slap or a smile. Now there is one small difference between a computer and your friend. Computers are really stupid. They are like a 3-year-old kid. So even if you have told the computer as to what it needs to do, you would have to tell it step by step as to how it needs to be done. So the task that the computer has to perform has to be explained to it in every step. So for example, in case of proposing, a 3-year-old kid does not know what proposing means. You'll have to exactly tell him as to what words to tell the girl, how to do it, maybe take a chocolate, maybe take a bunch of roses, but you will have to tell him every step that he needs to do. That's exactly how computers are. So the function of a computer is very simple. It's a device that can perform tasks for you really fast, but you need to instruct it every step that it needs to do. Now we know what a computer is. Let's see what is inside this computer. Okay, so what is a computer made of? We know that the heart of the computer is the CPU. Also, you can see that you have something called the keyboard or the mouse right in front of you. So the keyboard or the mouse are the input devices. And then you have the monitor, which is your output device. Also, you have heard of the term called RAM or random access memory, which is also called the main memory. Now we know what the computer is made of. So let's see how these components interact with each other. The CPU, as you know it, is the heart of the computer, and it is responsible for executing all the instructions that are given by you in the form of a program or an application. The program or the application could be sitting on a hard disk. The hard disk acts as both an input or an output device, because you can get instructions from the hard disk, and at the same time you can also store the results on the hard disk. So let's say you have a program stored on the hard disk. The CPU would fetch the instructions from the hard disk and copy the instructions to the main memory. It would then fetch one instruction at a time from the main memory and execute it. During this whole process, the CPU also uses the main memory to store intermediate results. Now you might wonder as to why do we need the main memory when everything we need is already present on the disk. The CPU could just read the instructions from the disk directly and store intermediate results on the disk too. Then why do we need the main memory? The speed of the main memory is many times faster than that of the hard disk, making your applications run really fast. If the CPU were to fetch all this from the hard disk every time, then the applications today would be 1,000,000 times slower. Now, what is the purpose of the input or the output device? The instructions that the CPU needs to execute is going to come from the input device, which could either be directly from the user from the keyboard, or it could come from a hard disk too. And finally, after all the processing, the CPU needs to send the output somewhere, which could be a monitor or the hard disk again, which is again an output device. Now the input that comes to the CPU consists of two parts. The input consists of the data and the instruction. What do we mean by these two terms? Let's say you want the computer to add 45 and 56. The instruction that you're giving to the CPU is add two numbers. The data you're sending the CPU are the numbers 45 and 56. So any instruction or any input that comes to the CPU always comes in two forms. That is the data part and the instruction part. I have now given you a quick summary of the basic components of a computer. Now, while writing programs, the most important part you need to worry about is the main memory, as everything finally sits in memory before it is executed by the CPU. So let us try and understand what the memory looks like. For this, let's imagine a huge piece of land. Okay, consisting of equal size plots. Let's say there are about 200 plots on this piece of land. And each of these plots are numbered starting from 1. So this is plot number 1, you have plot number 2, you have plot number 3, and so on until plot number 200. So now a house constructed on plot number 1 would have the address 1. Similarly, a house constructed on, let's say, plot number 20 would have the address 20. Of course, some people want a bigger house, so they may buy 4 plots together. So let's say somebody who wants to construct a big house buys the plots 65, 66, 67, and 68. Then his house address is of course 65 because his plot starts at number 65. The next person who wants to purchase a plot buys plot number 69 and his house address is 69. The main memory looks exactly the same. It's like a huge piece of land, consider multiple plots, but in this case, it's of equal sized plots are called cells or bytes. So the main memory also consists of equal sized cells and they're called bytes. The difference is the numbering here starts from 0. So the first cell is 0, then 1, 2, 3. So if you have a memory of 1 kilobyte in capacity, 1 KB is nothing but 1024 bytes. In that case, the numbering would go from 1, starts from 0, and will go up to 1023. The last byte would have the address 1023. 0 to 1023 is nothing but finally 1024 bytes. So this is what the memory would look like for a RAM with 1 KB capacity. Now each cell or byte in memory consists of 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Each of these bits can either store a 0 or a 1. So if you look at the entire main memory, it only consists of zeros and ones. It's these zeros and ones put together that give us meaningful data that is stored at a particular location. So let's say I want to store the number 15 at address 6. So we have 3, we have 4, 5, 6. So at this location, address 6 would mean it's actually the 7th byte. 2, 3, 4, 5, 6, 7. Because the numbering starts from 0, the 6th address is actually the 7th byte. So let's say I want to store the number 15 at address 6. Then what you will see in that cell or byte would be the number 00001111. That is the binary equivalent of the decimal number 15. So finally at cell 6, the 8 bits would contain, the first bit will be 0, the second bit will be 0, third bit will be 0, the fourth bit would be 0. The 5th, 6th, 7th and 8th bits would all be 1s. So as you can see, the main memory is similar to a large piece of land with multiple plots, with each of the plots numbered in sequential order. Now that we've understood what the memory is made of, let's move on to understand the heart of the computer, which is the CPU. You might have heard of 32-bit and 64-bit CPUs. To understand many concepts of programming, we need to understand the difference between a 32-bit and a 64-bit CPU. The meaning of a 32-bit CPU is that the CPU itself, so this is our CPU, has about 32 bits to store an address location. 32 bits means 4 bytes. So we have about 4 bytes in our CPU to store some address location which is in memory. Now what is the purpose of these 4 bytes? To understand this, we need to understand some basics about bits. A single bit can either store a 0 or a 1. I cannot represent the numbers 2, 3, 4, etc. using a single bit, because to represent the number 2, I need 2 bits. To represent number 3, also I need 2 bits. To represent number 4, I need 3 bits, and so on. So with just 1 bit, I can only represent the number 0 or the number 1. The largest number I can represent is 1, which is nothing but 2 to the power of 1 minus 1. The symbol over here is to the power of. Now similarly, let's say we have 2 bits. With 2 bits, I can represent the numbers 00, 01, 10, 11. So I can represent 4 different numbers, and the largest number I can represent is the number 3, that is 11, which is nothing but 2 to the power of 2 minus 1. So similarly, let's say I was given 3 bits. As per this math, the largest number I can represent is 2 to the power of 3 minus 1, which is 2 to the 4, 4 to the 8 minus 1 is 7, which is also correct because with 3 bits, the largest number you can represent is 111. In decimal, this is equivalent to 7. So going by the same math, if you have n bits, the largest number you can represent using n bits is 2 to the power of n minus 1. To have a better understanding of the binary number system, kindly go to the Wikipedia page for the binary numeral system. Now, if your CPU has 32 bits to store an address, the largest address it can store is, you just learned, with 32 bits, the largest address you can store is 2 to the power of 32 minus 1. This is the largest number the CPU can store in the 4 bytes that it has. This is nothing but 429,496,7296. This means we can have a memory with so many bytes, which is nothing but 4 GB. Hence, with 32-bit CPU, you can only have a maximum RAM of 4 GB. But these days, 4 GB is hardly enough to play games or make movies. This is why we now have 64-bit CPUs. This has helped us to have memory that can go beyond 4 GB and can go up to 2 to the power of 64 minus 1, which is extremely large number and should suffice for a number of decades to come. The CPU basically fetches all your instructions or the data from main memory. The address from which it has to fetch are stored on these 4 bytes. So with just 32 bits, the CPU can go up to an address of 4 GB. If the main memory was greater than 4 GB, it can never access that part of the memory as it cannot store that address in its memory location. To understand this better, let's analyze a real-life scenario. Let's go back to our example of the land. So I have a huge piece of land with about 200 plots. Now I send a 3-year-old kid to this huge land and asked him to go to plot number 145, let's say, which is over here. The plots are all numbered sequentially, so it should not be a problem finding plot number 145. But the problem is that this 3-year-old kid does not know counting beyond 99. So if you send him to this plot, he would go sequentially and he would stop at plot 99. After that, the numbers 100, 101, 102, etc. do not make any sense to him. So he has no idea what to do. This is exactly how a 32-bit CPU is. 32-bit CPU knows counting until 4 GB. After 4 GB, the CPU cannot store the address in its memory. So all the memory beyond 4 GB would be useless. So now you understood the difference between a 32-bit CPU and a 64-bit CPU. To be a great programmer, you really need to understand the binary number system. So please don't forget to go through the Wikipedia link provided earlier. This chapter, we're going to teach you the basic difference between giving an instruction to a friend and giving an instruction to a computer. As we had discussed in the previous chapter, you need to think of a computer as a 3-year-old kid and break down your instructions to the smallest step possible. So we're going to take a real-life example to help you understand what I mean by breaking down the instructions to small steps. In this chapter, we're going to learn two basic concepts. One, given a task, how to break it down into small steps, and the necessity to actually break it down and write it down as an algorithm. So before we start explaining the concepts, let's take a real-life example. Okay, so let's say your semester results have just been announced and you're unable to go to college to see your rank. So you ask your friend to check your rank on the college board. So you have a board in college. Basically, starting from rank number 1, it'll have names. The first name has a rank number 1, second name has rank number 2, and so on and so forth. And the task here is your friend has to go up to the board, search for your name, check what the rank is beside it. So this is like 1, 2, 3, 4. Search for your name in this board, check what the rank is, and come and tell you. So let's see how would you give these instructions to your friend. I'm going to split the screen now in two halves to show you in one half as to what the steps are going to be to your friend, and the second half we're going to talk about how the steps are going to be explained to the computer. Okay, this half we're going to have the instructions to a friend, and here on the right side we'll have the instructions to the computer. Okay, so let's first start with the instructions to a friend. The first thing you're going to tell him is go to the college board. What is the second step he needs to do? Search for my name on the board. And finally, check the rank against my name. That's it, and the task is done. So these are your instructions you would give to a friend. You don't have to explain anything more than this. Now, the same instructions will not work with the computer. Let's see why. Go to the college board is okay. You can, if a computer understands this, or even let's say we're talking about a 3-year-old kid, you can tell him, go up to the college board, which is fine. Now the problem is with the second step. When we say search for my name, the term search does not make any sense to a computer. He does not know what search means. Or let's say a 3-year-old kid who doesn't understand the term search. What are you going to tell him? How do you explain to him? If you just tell him go search for my name, what does he do? He doesn't know. He may just randomly stare at the board and come back. So the second step needs to be broken down into smaller set of steps to explain what we mean or how to actually search for the name on the board. So now let's see how we write the instructions to the computer. Okay, the first step to the computer is similar. Let's say go to the college board. The second step, like you mentioned, search for my name, will not be understood by the computer. So you will have to break this down. How do you break down search for my name? We go to tell it one by one. What does it need to do? Read the first name on the board. Now if this name that he's read is your name, then good, check the rank and come back. If this is my name, see rank and come back. Now if this is not your name, what does he need to do? He needs to read the next name. So read the next name. What happens after he reads the next name? He needs to again check whether it's your name, so which is nothing but step 3 again. So we're going to keep repeating step 3 and step 4. Till what time? Till you find my name. So we repeat the above 2 steps until you find my name. So these are the instructions to the computer. So as you can see, we had to break down steps 2 and 3 into 3 extra steps. So now instead of 3 steps, we have 5 steps. But then the whole term search had to be explained, saying how do we search. So as you can see, we have now explained the steps of how to search for a name. Breaking down of a task into smaller steps is called an algorithm. So basically an algorithm is the steps of how to solve the problem. For any program that you're asked to write, you should know of 3 things. What does the program need as input? 2, what is the task to be performed by the program? And 3, what is the output expected from the program? Once you have these 3 things, you can write an algorithm in plain English for the task that needs to be performed. So in the example above, input was my name. The task was to search for my name. And finally, the output is my rank. It's always a good practice to write down the algorithm before you start writing the program itself, as an algorithm is always in plain English, and as humans, it's easier for us to think in English rather than in a programming language. So once you have an algorithm in place, each step in the algorithm would get converted to a line or a set of lines in your programming language. Okay, to get the concept of algorithms more clear, let's try a few more examples. The next example would be to tell a friend how to boil water in a kettle. Boil water in a kettle. Before we start writing the algorithm for this, we first need to figure out 3 things, like I mentioned earlier. First, we need to know what the input is. In this case, we know that the input is the kettle itself, and there is water. Now, what is the task to be performed? There are 2 tasks here. Boiling water is one task. And what is the other one? We need to fill up the kettle with water. Fill up the kettle. And finally, we have the output. In this case, the output is boiled water. Like in the previous example, we're going to first start with instructions to a friend. The instructions to a friend are pretty straightforward. 1, you just ask him to fill the kettle with water. Water. 2, place it on the stove and turn on the burner. And finally 3, turn off the burner when the water starts boiling. Starts boiling. The last 2 steps basically tells you about the task of how to boil the water. The first step tells him to fill up the kettle with water. Now again, like I said earlier, these 3 steps will not work for the computer. Why? Mainly because the task fill the kettle with water does not make sense. When you say fill up the kettle with water, the computer does not understand what you mean by fill up. A fill up could be 100% to the brim, it could be 98% of the kettle, 90% of the kettle, it could be 50% of the kettle. When you're talking to a computer, you need to specify exactly how much water you need to fill up. So the first step needs to be broken down. Place it on the stove and turn on the burner is straightforward. Then finally turn off the burner when the water starts boiling. To the computer, you need to define again what is boiling. In this case, we say turn off the burner when the water hits 100 degrees Celsius. So let's see how the instructions to the computer are. So first task, fill up the kettle with water. You need to break it down. So if you have to break it down, what are the first tasks now? Put the kettle under the tap. Under the tap. Now what's the second step? Turn on the tap. The third step will be check if the kettle is filled with water. What do we mean by filled with water? In our case, we'll say 90% of the kettle, then we turn off the tap. So check if the kettle is filled to 90%. If it's not, we just say repeat the above step. So he'll keep repeating the above step until it's filled with 90% of water. Once that's done, say close the tap. Now we've done the first step of filling the kettle with water. What's next? Place the kettle on the burner. The burner. Then we have turn on the burner. Now the final step again, we need to specify what we mean by boiling. So we just check if the water is 100 degrees Celsius. If it's not, repeat the above step. If the water has touched 100 degrees, we just have to turn off the burner. So these are the steps that you're going to tell the computer if you need it to boil a kettle of water. So as we had explained earlier, first we started with breaking down the problem into input, the task, and the output. Once we had the three data in place, we then sat down and wrote the algorithm for the task to be performed. The two tasks were filling up the kettle with water and boiling the water. So we wrote the algorithms for both of them, and you put the steps together, you had the entire problem solved. Okay, so let's do one final example. The reason we are doing this so many times is because beginners generally have one tough problem, which is grasping the concept of steps or algorithm. They always wonder, why do you need an algorithm? Given a problem, they start thinking of writing the program directly and fail miserably because your brain does not work like a program. So once you break down the given task into a set of steps in plain English, then mapping each step to a code makes it very simple. So let's take one final example which may go for the ladies. So let's say we want to go shopping on MG Road. We want to buy a red colored shoe with maybe a bow on it, and from the Bata showroom on MG Road. So let's call this shopping on MG Road. What is the first thing that we need to do? We need to know what is the input. In this case, input is Bata showroom, that is the name of the shop, and we have MG Road, so we have the name of the road. Then we have the color of the shoe, which is red. We could describe other stuff like shiny. Let's not make it complicated, so let's stick to a red shoe, and let's say we want size 5, so size of the shoe. So we have the input. What is the task? The task is to go shopping. And finally, what is the output? Output is the shoe itself, if you find it. Now, before we start writing the algorithm for the task, let's look at the problem diagrammatically. So let's say this is your road. This is MG Road. And you have shops along the side. Multiple shops. And this is your friend who's going to start shopping from the start of MG Road. So what's he going to do? He's going to basically walk down MG Road, looking at one shop at a time. And when he finds, let's say this is the Bata showroom. When he finds the Bata showroom, he goes in, asks them for the shoe that he's looking for, and walks out if he finds it. The task is simple. So if you were to ask your friend to do it, you're just going to tell him, go to MG Road, go to the Bata showroom, find me a red colored shoe, size 5, and come back. Simple and straightforward. So I'm not going to spend time writing the algorithm for a friend. So let's start with the algorithm for the computer. Okay, so what is the first thing that the computer needs to do? Walk to the first shop on MG Road. What is the next step? Check if this is a Bata showroom. If it is, then you enter the shop and ask for a red shoe size 5. If he has it, you buy the shoe and come back. Now what if this was not a Bata showroom? In that case, you just go to the next shop. And then you go back to repeat from step 2. Go to the next shop. Again, you check if there's a Bata showroom. If it is, you enter the shop, ask for a red shoe size 5, buy the shoe and come back. If it's not a Bata showroom, you again go back. You come to step 5 and then you go back to step 2. Okay, the reason I'm making you practice writing algorithms is that given a problem for a programming language, you don't have to really write down the algorithm on paper, but if you have the algorithm in your head, you can easily convert it to a program. But without an algorithm, writing a program becomes extremely difficult. So getting the algorithm in your head directly is not such an easy task. So the best way to start doing it is, given a problem, start writing it down on paper. Write the algorithm, write what is the input required to the program, what is the task to be performed by a program, what is the output required from the program. Now write the algorithm for the task that you're going to perform. Once you have it all on paper, converting it to a program becomes a very simple task. And make it a habit to always put down the algorithm on paper so that over a period of time, it just comes to your head automatically and you don't have to worry about thinking of every step. Every step will be automatic in your head. Just to get used to this, just pick up any real life example and try to convert it to steps that you have to give to the computer to perform the exact same task. Practice it with daily tasks like go shopping for vegetables, break it down to tasks. Just try a few examples on your own and see if you're satisfied with what you've written, that it's small enough. Say, if you give it to a small kid and ask him to read it, he knows exactly what he needs to do. If it works, then you're almost getting there. Then when we start talking about the C language or any other programming language, you easily know how these steps get mapped into the programming language.